So let's look at solving some titration problems. With a titration, you're actually trying to reach that neutralization point of an acid and a base to determine an unknown concentration of one of them. In our equipment, we will use a burette, which is an accurate way of measuring a volume, which has a stopcock, so we can actually stop the flow. We'll have a conical or Erlenmeyer flask in which we will actually place the analyte. So the analyte is the thing that is unknown concentration that we're trying to work out. So we'll put a known volume in with a suitable indicator. We'll then measure the volume of titrant required to actually reach that equivalence point, which is when it is at neutral. So the only thing in the solution is our water and salt in the solution of the analyte. So let's start with a problem in terms of hydrochloric and sodium hydroxide. And we've been told that we had 100 mils of hydrochloric, and this is obviously our analyte because that's what we're adding the phenolphthalein indicator to. And it used 75 mils to reach that equivalence point. And notice here I've said the question says endpoint. The endpoint is a little bit different from the equivalence point in the fact that it's when you stop the titration. So that's when you actually have a color change, whereas the equivalence point is that exact. Now the endpoint and the equivalence point need to be really close together in terms of that volume. So it's normally we'll try and get it within half a drop. And that's why we can use either measurement. So they determine the concentration of the hydrochloric acid. So the first thing to do in any problem is to actually write out the equation of what's actually occurring. So when hydrochloric acid reacts with sodium hydroxide, they're both strong, it's going to form water and the salt. At the moment, this is fully balanced, so I don't need to add any coefficients, which means it's a 1:1 ratio between the acid and the base. And that's actually important because at the equivalence point, it isn't an equal number of moles, it's an equivalent number of moles. The ratio between the acid and the base is actually very important. So 1:1 here. So in terms of our formula and data booklet, we have the aqueous solutions and acidity. We've been given that molarity or concentration is equal to the moles of solute. So I like to write this as C equals N/V. Other people like to use a capital M. Either way is fine, as long as you're consistent throughout. So this can be rearranged to be the number of moles. So the number of moles equals the concentration times the volume. So we're going to use this because what's actually happening is at equivalence point, the concentration of the volume of the acid divided by the number of moles of the acid, so we use that entire formula, is the same or equivalent to the concentration and the number of moles of the base. So in this case, it's 1:1, so we don't even need to divide by the ones. So we then just need to substitute the values that we've been given. So we're trying to work out the concentration of the acid, so we have to leave that there, but we were told the volume. So we multiply by the 100. It's going to equal the concentration of the base, so 0.15 multiplied by the 75. To be fully correct, in terms of if you find it easier to always convert to the volumes that we should be using, which is litres. If you find it easier to always do your conversions to litres because you don't want to have to remember in situations where you don't have to, then always convert. But in this particular case, because on both sides we're actually going to divide by 1,000, they'll cancel each other out. So technically we don't need to. So then it's a case of rearranging. So because it was a multiply on this side, it's going to be a divide. So the concentration of acid is going to equal the 0.15 times the 0.075 over 0.1 to give a concentration 0.1125 molar. So then it's going back and checking, have I actually done all the information that I need and did I substitute correctly? So you should always go back and check that you've actually used the correct volumes in the correct ones and that you've actually answered the question. So in this case, the question was determining concentration of the HCl, which was our acid, which is the answer that we've got. So we have done that. There was no other part of the question. We used the 75 mils for the base. We used the 0.15 for the base. We used the 100 for the acid. So everything else is correct. And it never hurts to do a final check in terms of your answer calculation. So let's look at a separate sort of problem. Sometimes you won't be given it all the information in the actual word problem. You'll actually be given some of the information in a titration curve. So remember, a titration curve, that equivalence point or end point is, the equivalence point is halfway. The end point we probably would have stopped around here. So we could have stopped anywhere within this straight up area, which is the equivalence region. The reason for that is that that's where we would have to be choosing a pH indicator that actually was within this area and had a clear delineation of only changing colour within that area. So it didn't stop too early or too late. So in this case, I'm going to estimate that this was 16 mils for that volume in terms of what was required. So that then would become the volume of sodium hydroxide or the titrant that I had to add. This question has been also a little bit complicated in the fact that there's also a dilution. So we don't always have just a straight titration. Sometimes we'll have a dilution. The key to solving these types of questions is to consider everything that was a dilution in one part of the question and do that last, and everything that was the information about the titration, do that first. So I'm going to highlight these in different colours. So my dilution information, so it was given 10 mils, so my dilution volume is 10 mils, and it was diluted to 200 mils. And this is important because this is its the real concentration and its initial volume, and this is what it ends up with. So it's its final concentration and its second volume. So we're going to use this later. So all this information here I'm not going to use, whereas the second part of the question has the information about the actual titration. So 20 mils is my volume for the titration. So for the titration, my volume is going to be 20 mils. And it was titrated against 0.10 molar NaOH. So that's my concentration of my base. This is my acid. And my volume of my base, I have to read from the graph, which was the 16 mils. So then I have to determine the original concentration of the acetic or ethanoic acid in the vinegar from its titration curve. So we do that in the same way as we did before. So the first thing we do is we write out our equation. And in this case, it's a weak acid with a strong base. Therefore, we're going to need the equivalence arrows. So it's going to become our water plus our sodium acetate. And again, we have a 1:1 ratio. Therefore, we can just use the concentration of the acid times the volume of the acid equals concentration of the base times the volume of the base. If you want to just use that same formula and be consistent every time, then you can. But this is 1 and 1, so we don't really need them. So in this example, I'm not going to do the divide by 1,000. So I'm just going to use the volumes that are there because they are all the same type of unit, which is mils. So remember, I've got to use my ones that only relate to the titration. So we don't know our concentration of the acid, that's what we're trying to work out. Our volume of the acid was 20. So that's going to equal our concentration of the base, which was 0.1, times the volume of the base used, which was 16. So our concentration of acid, if I rearrange, over 20, which equals 0.08 molar. So this is at the diluted acid. So our last step is to look after the dilution. So again, we can use our relationship that the concentration at the initial and the volume of the initial is going to equal the same number of moles in there as our concentration at the dilution and the volume of the dilution. So we now know the concentration of this because we've worked this out here. We know our volume, which is our 200 mils that it was diluted to. We know our initial volume, and we're trying to work out this initial concentration. So this is our question mark. So we can then just substitute in. So I can rearrange first, or I can just substitute in. So I'm just going to do the C1 times the 10 mils equals my concentration of the second, which is 0.08, times the 200 mils. So the concentration initial is my 0.08 times 200 divided by my 10, which equals 1.6 molar. So quite a high concentration in that vinegar. So we just need to check then, have we actually answered all parts of the question? So I've worked out should actually probably put initial concentration. To make sure I'm very clear in terms of my communication. So we can use our concentration symbols and our actual acid to help shortcut rather than having to write out a lot of words. So yes, I've answered the fact that it was the original concentration. To do that, I've used the check that I've done the correct volumes and the correct ones. So the 20 mils went into my acid. My 0.1 was from the concentration of the base. The 16 is from the volume over here, so those are correct here. And my final volumes, I had 200 and I had 10, so I've substituted incorrectly and I've used that correct concentration. So our last problem is just going to demonstrate why it's important to consider the ratio of moles. So in this particular case, I'm not using sodium hydroxide, I'm using calcium hydroxide, and we're again neutralizing hydrochloric acid. So let's write this equation out. Remember, writing the equation should always be your first step. Now in this case, we will have water produced, and our salt will be the calcium chloride. But in this case, it's not balanced. I'm actually going to need 2, and we can actually determine that because of the OH2, we'll be able to neutralize 2 HCls. It's also because the calcium chloride, I need 2 chlorides. So in this case, I've actually got a 2:1 ratio rather than a 1:1 ratio. So remember I said it's important to actually think about writing that number down in terms of the number of moles and then determining whether you need to use it, or even just writing in the fact that it's 1 and 1 in terms of your molar ratio. So you should write your balanced equation, then explain that it's a 2:1 or 1:1 in whichever case. So then it's a case of then substituting in, but down the bottom it's going to be 2 because of the number of moles of the acid and 1 here. So we were told that we had 50 mils, so 0.250 divided by 1,000 is 0.05. So let's make everything in litres in this particular case. So that was our volume of our base, and we had 0.5 molar, so our concentration. The second one, we don't know our concentration, and we had 125 mils, so 0.125 when I divide by 1,000, and then we have to divide that by 2, in which case, when I'm rearranging, it's going to be take the 2 because it was divided and multiply, so 2 times 0.5 times 0.05 and divide by 0.125 to have our final answer of 0.05 divided by 0.125 of 0.40 molar. And then we need to, and this is again our concentration of our HCl. So this is the simplest way of doing them. You can work out the number of moles that were actually in the base and then work out that that would be the same number of moles and take into account that you actually needed 2 moles, that will be half that number of moles required in this one. And that requires additional steps. So the simplest way of doing it is working through here to have the minimum number of steps, and the fastest way of doing it.